Here's a quiet problem hiding in plain sight. Every day, across the internet, encrypted data is being recorded and stored by adversaries. Bank traffic, medical records, legal archives. It looks safe today, but a future machine could unlock it years from now. That future machine is a large, error-corrected quantum computer able to run a specific algorithm called Shor's, and that's why post-quantum cryptography is getting rolled out now, before the break happens. So what is post-quantum cryptography? It's a new generation of encryption and digital signature algorithms designed to stay secure even if powerful quantum computers arrive. It doesn't need a quantum computer to run. These algorithms are regular software that runs on laptops, phones, and servers. The difference is the math under the hood. Instead of relying on problems like factoring big numbers, the trapdoor that RSA uses, these new schemes are built on problems that aren't known to crack under quantum attack. The reason to care is simple and practical. If data needs to remain confidential for years, maybe decades, waiting until a quantum computer exists is too late. Anything recorded today could be decrypted later if today's algorithms are still in use when that moment arrives. Think of RSA like a safe whose lock is the product of two huge primes. Locking it is easy. Unlocking, factoring, is excruciatingly hard for normal computers. A large quantum machine running Shor's algorithm is like a magical scanner that reveals those two primes, so the safe pops open. PQC replaces that safe with a different kind of lock. A helpful mental picture is a high-dimensional haystack built from a grid called a lattice. The secret is a tiny, short direction inside that haystack. To anyone without the key, the haystack looks noisy and uniform. Even a quantum scanner doesn't have a shortcut to find that one tiny needle. Lattices, by the way, are just regular repeating grids in many dimensions, like a three-dimensional honeycomb extended into higher dimensions. So the simple version is, today's public key crypto depends on math that a future quantum computer could demolish. Post-quantum crypto depends on math that appears stubbornly hard even for quantum machines. Let that settle for a moment. This isn't about hype, it's about timelines. Now for a bit of grounding. Quantum computers today are lab-scale and noisy. They can't break RSA 2048. The issue is the migration window. Large organizations take years to change cryptography across browsers, servers, apps, hardware, and supply chains. That's why standards bodies and companies are moving now. The U.S. National Institute of Standards and Technology, NIST, has standardized a set of post-quantum algorithms after a multi-year global competition. Two names matter most for daily internet use. CRYSTALS-Kyber is for exchanging secret keys over a network. It's called a key encapsulation mechanism, or KEM. CRYSTALS-Dilithium is for digital signatures, proving a server or document is authentic. There are also alternatives like Sphinx Plus for signatures and ongoing work on others, but those two are the headliners. Here's the thing. These algorithms are designed to drop into existing protocols like TLS, the same plumbing used by HTTPS. That means browsers and servers can start mixing post-quantum and classical methods during a transition, gaining protection without ripping everything out. Before diving into how Kyber works at a high level, it helps to understand the threat it's built to resist. RSA and elliptic curve cryptography, ECC, depend on problems that are tough for normal computers. Factoring large integers for RSA and the discrete logarithm problem for ECC. Shor's algorithm turns both into solvable tasks on a sufficiently large quantum computer. Secure keys become recoverable from public information. In other words, the very thing that makes public key cryptography useful, the ability to share a public piece widely while keeping a private piece secret, stops working. That's the cautionary side. The good news is the alternative looks solid. Lattice-based cryptography, which underpins Kyber and Dilithium, relies on problems like learning with errors. The name sounds technical, but the idea is accessible. Imagine publishing a bunch of simple equations that almost reveal a secret, but each one is dusted with a tiny amount of random noise. If you don't know the secret, those little errors add up like static. If you do know the secret, you can cancel the noise and read the message. The best-known quantum algorithms don't clear that static efficiently. The key idea is that noise is a feature, not a bug. Here's a high-level tour of what Kyber, the key used for key exchange, does in practice. A server generates a public key and a private key. The public key encodes a structure built from a random lattice and a hint that is intentionally blurred by small errors. The private key is a short secret vector that fits that structure. That's the only specialized term needed. A vector here just means a list of numbers, like coordinates. When a client wants to establish a shared secret with that server, It takes the server's public key, mixes in its own randomness, and produces a small ciphertext plus a secret number that will become the session key. That ciphertext is carefully constructed so that only someone with the private key can remove the blur from the public hint and recover the exact same secret number. Anyone else just sees a pile of numbers with noise on top. Put differently, the rightful receiver has a pair of noise-canceling headphones. Everyone else hears static. This is called encapsulation on the sender side and decapsulation on the receiver side. Under the covers, there are matrix and vector operations, but the flow mirrors what RSA did for years: exchange a fresh shared secret over an untrusted network. The difference is, the math is built from lattices and noise instead of factoring large primes. There's an engineering elegance to this. Hiding a tiny, structured secret inside what looks like random linear equations and making it recoverable only with the right short key shows careful design. The fact that it runs fast enough to handle modern internet traffic on ordinary CPUs is a testament to how much optimization has gone into these schemes. Now back to the practical world where products ship and outages hurt. The deployment path most organizations are following is hybrid. In a TLS handshake, a server can offer both a classical key exchange, like X25519, and a post-quantum one, like Kyber. The client performs both and combines the results. If a future quantum computer breaks the classical half, the session is still protected by the post-quantum half. And if any intermediary device or client doesn't fully support the new algorithms yet, the classical half keeps the connection working during the transition. A concrete example helps. Picture a bank's website serving millions of customers. The server presents a normal certificate chain for identity, and it supports a hybrid key exchange. A customer's browser connects and receives the server's classical public key and its Kyber public key. The browser uses the Kyber key to encapsulate a fresh random secret and also runs the classical exchange. Both outputs are combined into the session keys that encrypt the web page and transactions. The server uses its Kyber private key to decapsulate the post-quantum part and completes the handshake. Even if someone records the traffic today and waits for a quantum computer to break the classical exchange in 10 years, the Kyber part keeps the session undecipherable. What's the cost? Post-quantum keys and messages are larger than ECC. A Kyber public key is on the order of a kilobyte, and the ciphertext returned by a client is also around that size. In a browser handshake, that might add roughly 1 to 2 kilobytes of data compared to classical-only exchanges. On modern networks, that's usually a rounding error. On constrained IoT links or high-frequency APIs at hyperscale, that overhead needs planning. Computation is heavier too, matrix-style arithmetic instead of small elliptic curve operations, but efficient implementations keep it within practical limits for most servers. Signatures are the other half of online trust. A server certificate, code updates, and documents rely on digital signatures to prove authenticity. Dilithium, the lattice-based signature standardized by NIST, fills this role. It creates and verifies signatures quickly, but the signatures are larger than ECDSA. As a backup, Sphinx ES Plus exists with different trade-offs. It has smaller public keys and is based on hash functions, but signatures can be larger and verification slower. In practice, certificate authorities and vendors are working toward issuing PQ-capable certificates and exploring ways to bridge the gap, including transitional mechanisms that carry both classical and PQ signatures during early rollout. There are a few common misunderstandings worth clearing up briefly. One is that post-quantum cryptography somehow protects everything about cryptography from quantum attacks. Symmetric algorithms like AES, which encrypt data once the session key is established, survive just fine by doubling key sizes. A 256-bit AES key is still considered safe even with a quadratic quantum speedup called Grover's algorithm. The real urgency sits in public key methods like RSA and ECC that underpin key exchange and signatures. Another misconception is that quantum computers today can break RSA 2048. They can't. Current devices have too few error-corrected qubits to run Shor's algorithm at the necessary scale. The point is to finish a safe migration before a capable machine exists, not to panic because it already does, and the idea that harvest now, decrypt later is only a government problem misses the mark. Any organization that handles data with a long shelf life, healthcare records, legal contracts, product designs, genomic data, needs to think ahead. Zooming out, the standards and policy side is also moving. NIST's selections, Kyber for key exchange, Dilithium for signatures, plus others, came after years of public cryptanalysis and tuning. Security agencies have advised hybrid deployments in sensitive environments. Cloud providers and CDNs have trialed and, in many cases, enabled post-quantum options in front doors that handle vast amounts of traffic. Browsers and libraries have implemented draft extensions to negotiate hybrid key exchanges. This is no longer a lab experiment. So how does an enterprise move without breaking things? A sensible approach starts with visibility, inventory where public key cryptography appears, TLS for websites and APIs, VPNs, SSH, S-MIME and code signing, device firmware updates, internal service meshes, and stored data that relies on keys for access. Many teams discover crypto hiding in libraries and vendor products rather than directly in their own code. The next idea is crypto agility. That simply means building systems so algorithms can be swapped without a full rewrite. Using well-supported libraries that already offer post-quantum options helps here. It also means setting policies that avoid hard-coding specific algorithm names deep in configuration files or protocols where they can't be changed later. Pilot projects are where learning accelerates. A common place to start is enabling hybrid key exchanges on a subset of TLS endpoints, perhaps in staging, then in a canary share of production traffic. Measure handshake sizes, connection latency, CPU load, and any failure modes with older clients or middle boxes. Some organizations publish public test endpoints so external clients can try PQC handshakes without risk. From there, plan a phased rollout with customer-facing services first, then internal APIs, and higher-risk systems like VPNs as vendor support matures. For signatures, coordinate with certificate authorities about timelines for issuing PQ-capable certificates, and test code signing and firmware pipelines end-to-end. Monitoring remains essential because the ecosystem is evolving, standards and best practices harden over time, and staying current avoids surprises. What about trade-offs and limits? Larger keys and signatures are the most visible. A Kyber public key is roughly 800 to 1300 bytes depending on the security level, and ciphertexts add similar amounts. Dilithium signatures can be a couple of kilobytes. For most web usage, that's acceptable overhead. For devices with tight bandwidth or memory budgets, careful engineering, parameter choices, and sometimes protocol tweaks are needed. Computation is also higher, though still very manageable on modern CPUs. Hardware accelerators and optimized libraries help in high-throughput edge cases. Side channel resistance, ensuring that timing or power draws don't leak secrets, requires the same discipline used for classical crypto: constant time code, hardened randomness, and thorough audits. A useful mental checkpoint is that post-quantum cryptography is not a silver bullet. It addresses a specific class of threats. Quantum attacks on public key primitives. Strong operational security still matters. Keys need to be generated and stored safely. Randomness must be high quality. Protocols should be configured sensibly. And for symmetric encryption and hashing, existing algorithms with appropriately longer keys remain in the picture. One more realistic detail helps anchor expectations. In a hybrid TLS 1.3 handshake using Kyber along with a classical method like X25519, the overall time to establish a connection is often within a small margin of classical-only handshakes on modern networks, often a handful of milliseconds difference. The bandwidth overhead tends to be around 1 to 2 kilobytes for the exchange. For a typical web page, that's negligible. At the same time, an API doing tens of thousands of new connections per second on a single host might see a CPU bump, prompting load balancing or hardware choices. These are optimizations, not showstoppers. There's a quiet moment of appreciation here. The research community and engineers have taken deep, abstract math and turned it into working building blocks that slot into the global internet. That kind of translation, from theory to standards to code, is rare and worth noting. A final word on timing. No one can put an exact date on when a cryptographically relevant quantum computer will exist. Estimates vary, and credible timelines still point to years of hard engineering work. But migrations at scale take years too. Data with a long life needs protection that lasts beyond its creation date. Planning and staged adoption now is the steady, low-drama way to avoid urgent scrambles later. For individuals and smaller teams, the path is similar, just scoped down. Use mainstream libraries and runtimes that include post-quantum options. Track vendor roadmaps for browsers, operating systems, and cloud services. Enable hybrid modes where available. And when a system handles information that needs to stay secret for a decade or more, prioritize those upgrades earlier. To wrap the mental model one more time, Classical public key crypto is like a safe whose combination is the product of two giant primes. A future quantum machine learns that combination quickly with Shor's algorithm. Post-quantum crypto shifts the lock to a different world, finding a tiny, short direction in a huge, noisy, high-dimensional grid. That search looks intractable even for quantum computers as far as current knowledge goes. Standards have converged on algorithms that implement this idea cleanly, and real systems are already integrating them in hybrid form. The stakes are human, not abstract. It's about keeping a child's medical history private when that child becomes an adult. It's about ensuring a small company's designs aren't exposed to a competitor a decade from now. And it's about the internet staying trustworthy as the underlying physics of computation takes a leap. If this helped clarify how post-quantum cryptography replaces RSA before it breaks, a like and subscribe helps more explainers reach the people who need them.